Hello, everyone. I'm Leo, and I'm very glad today to introduce you to our work on combating false negatives in generative adversarial imitation learning. So this work was performed at Mila, and I was very glad to be part of this amazing team. The motivation of our work stands in the reinforcement learning world, where it's often impossible or impractical to get access to ground truth reports. However, sometimes we have access to expert demonstrations, and the goal is to leverage these demonstrations in order to train policies. A popular method is generative adversarial imitation learning. However, there are several bottlenecks and it can be unstable. In particular, we identify a key problem with this methodology, which is the false negative problem that I will detail later. And we propose successful heuristics to improve the training procedure of Gale, generative adversarial imitation learning. So as a little bit of background, there are two traditional approaches in imitation learning. There is behavioral cloning, which you can understand as supervised learning. Given an observation, what is the optimal action to take? And there is also inverse reinforcement learning, where you want to recover first the expert's reward function, and then you do reinforcement learning using this reward function. And in 2016, Gale was proposed as an alternative method, and it works as follows. So you have a policy and an environment as usual, and you can generate trajectories. You also have access to expert trajectories, and you will feed those different trajectories to a discriminator. And the discriminator considers that the expert trajectories are positives and the generated trajectories are negatives. And this discriminator can produce rewards, and these rewards can inform the policy. So the more your trajectories look like expert ones, the more you should get high rewards. That's the hope. It works pretty well in practice. However, there are still bottlenecks. And one key problem is the false negative that we identify in this paper. So in the beginning, when you train an agent using Gale, there is a clear distinction between the expert and the agent episodes. So the expert are all successful, and the agent has poor performance at beginning because, of course, you are more or less random. And when you train, then the performance is improving until some of your agent episodes are actually successful. And you start seeing that, in fact, the discriminator can no longer assume that all the successful trajectories are expert trajectories. However, when you train the discriminator, we give a signal saying that those specific generated examples are negative ones, while they are actually successful. This is what we call the false negative problem. And we conjecture that it undermines the training procedure because it gives noisy signal to the agent. And we propose a diagnostic tool that we call oracle filtering in order to filter out all the successful agent trajectories using the ground truth rewards. So here, as I said, it's diagnostic. This is why we can use the oracle. And the conclusion is that when we remove the successful trajectories from the pool where we train the discriminator, we have tremendous improvement in terms of performance and also sample efficiency. However, the problem is that in practice, we don't have access to ground truth rewards, and this is just a diagnostic tool. And we propose fake conditioning as a practical solution to a false negative problem. And this is aimed especially, for example, for goal conditioned policies where an agent has to perform different tasks. So the way it works is that we are going to create adequate training data for the discriminator when there is a high amount of false negatives from the agent because it starts being successful. And the way it works is simple. We take a goal and trajectory and we replace the original goal from a randomly sampled one. So what happens is that now you have a trajectory that won't answer the right goal. So of course it's a negative sample because you are not completing the task. And we propose two specific possibilities for fake conditioning. Agent fake conditioning is adversarial. The way it works is that we train a discriminator, again, on both expert demonstrations and agent demonstrations. However, this time, we artificially replace the goal of the agent-generated trajectories, as I said. And it turns out that they will be, of course, true negative samples. Another possibility is to do expert fake conditioning. So this is no longer adversarial. Here we propose to train the discriminator on expert demonstrations only. And the original goal of the expert demonstration may have been replaced, meaning that again, we have created negative samples. So as such, discriminator would learn to distinguish whether a trajectory completes a given goal or not. So to give a little bit more of intuition of how it works, here is the typical environment where we perform experiments, which is baby AI. So you have an agent moving in a partially observable grid. And here, for example, you have to go to the purple ball. So let's say that this trajectory that you are seeing now is an agent trajectory. We can say that instead of going to the red ball, which is the original goal, go to the purple ball. There is no purple ball, so of course, this would act as a negative trajectory. And if it's an expert trajectory, same, we can replace the go to the yellow ball by any other object. For example, go to a blue ball. So this looks good, and maybe two solutions to solve the false negative problem, but there are still some bottlenecks to address. The first one with agent fake conditioning is that we no longer train the discriminator on trajectories where the agent was actually following the original goal. And the question is how this discriminator could identify if an agent actually accomplished the goal or not. Here is an example where if we replace the go to the red ball by go to the blue ball, the discriminator could immediately know this is a negative sample because there is not even a blue ball in the area. And it would not reward properly the agent that would go to the red ball because it would say that this is not answering the task, which is impossible. And expert fake conditioning, the problem is even more obvious, is that we don't train discriminator on generated samples at all. So what happens if there is an unknown behavior from the agent? The discriminator would not know exactly what reward signal to give. Fortunately, we also have solutions for those two problems, and we propose to train two additional discriminators to solve these two specific issues and provide auxiliary rewards that can help the agent whenever these problems arise. So how do these work? For the agent fake conditioning, what we propose is what we call DON detector. We train an additional discriminator on expert subtrajectories, and we want to predict if the goal has been completed or not in this expert subtrajectory. So the hope here is that this would provide a backup reward in case the fake condition agent trajectory is identified too easily as a fake one, because, for example, the goal, original one, was replaced with something that cannot be accomplished. So this discriminator would really specialize in giving reward if you accomplished the mission. And for the fake conditioning problem, we propose blank conditioning. So this time, we train a discriminator on agent and expert trajectories only, without any consideration for the underlying goal. So the hope here is that we can reward the agent trajectories that match the expert distribution in terms of behavior of how the agent is moving. And we do experiments on the baby AI environments, and we report here about 3 levels. You go to local, you have an agent that must go to a specific object, for example, a yellow key. Pick up lock, you have to pick up an object and understand where you are located with respect to this object. And put next local, you have to take an object and put it next to another one. And I want to mention that those environments are partially observable. So you need an agent that has a memory of what it has performed so far. And also the instructions are given in natural language, meaning that the agent must understand language and how it's associated with the different tasks to perform. And the architectures, the interesting part is that we need to process both the language instruction and the observation at the same time. And then we have to combine all this and use a recurrent neural network because, of course, we need to remember what happened in the past. So both the discriminator and the actor-critic policy are equipped with the capacity to understand language and vision data. So here are the results. We have many more tables in the paper, but here is the gist of what we prove. So those two environments were actually challenging, and the behavioral cloning or the baseline Gale are unable to succeed. So if you get 99% success, this is what we call succeeding level. And as I said, we introduce the diagnostic tool of oracle filtering. And clearly, if we remove all the false negatives, we have tremendous improvement. So the conjecture that we made looks like it's actually happening. The false negatives are undermining the training procedure. And by using the different scenarios where we can use agent fake conditioning, expert fake conditioning, the don't detector, and the blank conditioning, if we can do several different combinations, and in general, our method is outperforming even the oracle filtering and has very good success rates, meaning that we were able to propose significant solutions for the false negative problem. So the key conclusions for all the experiments we've made is that fake conditioning leads to nearly perfect agents, and all the variations using, for example, agent fake conditioning or expert fake conditioning, don't detector blank conditioning are all strong in general. And there is one that has sometimes a slight edge, and this is agent fake conditioning with don't detector. So in conclusion, this paper shows that the false negative problem is significantly hindering the performance of adversarial imitation learning. And we propose a general diagnostic tool, oracle filtering, to measure its impact. And I want to mention that this tool is not proper to baby AI environment. It can be applied to any other setting. And we propose fake conditioning to overcome the problem. And we significantly improve over the baselines for multi-goal tasks. And we also propose variations for single goal task where it's not possible, in fact, to replace the original goal with others. So we propose also variations for this in the paper. And in the end, we show that using auxiliary rewards with extra discriminators can further improve the agent performance. So in general, the gist is here, we have several discriminators that we can train, and we can use different combinations, and it's successful at solving the false negative problem. Thank you very much for your attention, and feel free to ask me any questions.